All right, so in this problem, it tells you in an experiment, a sample of an unknown pure gaseous hydrocarbon was analyzed. Results show that the sample contained 6 grams of carbon and 1.344 grams of hydrogen. Determine the empirical formula of the hydrocarbon. So they've actually made it really easy because they directly told you the number of grams of each of your elements. And so what you're going to need to do is to convert each of those into moles. So you'll go from grams of carbon into moles of carbon, grams of hydrogen into moles of hydrogen. And then once you've gotten your moles, remember those are going to be your subscripts, but because I want these to be whole numbers, the first thing we do in order to attempt to make them whole numbers is we divide by our smallest number of moles. And so the smallest number of moles here is 0.5. So I divide both of those by 0.5 and I end up with 1 mole of carbon and 2.667 moles of hydrogen. Well, 2.667 is not a whole number and you cannot round that to 3. So I need to figure out what I can multiply that by to get a whole number. And what you should realize is that if you multiply that by 3, you would end up getting a value that is very close to 8, and therefore we can round it to 8. So your empirical formula is C3H8. Okay? So you get 1 point for calculating the correct number of moles of carbon and hydrogen, 1 for the correct ratio, and then 1 for the finally for the correct formula. Keep in mind your empirical formula is the simplest whole number ratio of your number of atoms of carbon and hydrogen. So what I'm probably going to have to do in the next problem, or the next part of this problem, is determine the molecular formula. Okay, and remember you get your molecular formula by simply taking the molar mass of your molecular formula and dividing it by the mass of your empirical formula, which is C3H8. So let's see how they're going to get us to do that. Well, in B, it tells us that the density of the hydrocarbon at 25 degrees Celsius and 1.09 atmospheres is 1.96 grams per liter. Okay, so I covered up their work because I prefer it the way that I'm about to show you. I'm going to use Pivnert. And since I'm in grams per liter for density, I'm going to want to determine the number of moles. Well, I don't know the number of moles or the number of liters. So one assumption I'm going to make is that I am dealing with just 1 liter because it's 1.96 grams for every 1 liter. Well, let's figure out how many moles I have for 1 liter. So I plug in the pressure in atmospheres, 1.09. I plug in 1 liter. I plug in my R value, 0.0821, and I plug in my temperature in Kelvin, which is 298. And so when I solve that, I get 0.04455 moles. And that's 0.04455 moles per 1 liter, because I plugged in the 1 into my PV equals nRT formula. So it's asking me to determine the molar mass. So what I need to do is I need to take the density, which is in grams per liter, and if I divide that by the moles per liter, and you can actually look at my units, notice that the liters cancel, and the units that I'm left with are grams per mole, which is the units for molar mass. So I got 44 grams per mole. So you got 1 point for the correct substitution and 1 point for the correct answer. Basically, you get 1 point for your calculations and then 1 point for the correct units. Okay? In II, it says determine the molecular formula of the hydrocarbon. So I just talked about how you do that. So remember, you need to take the molar mass of your molecular formula, which we know is 44, we just solved for it, and divide it by the molar mass of your empirical formula. Well, our empirical formula is C3H8, which has a molar mass of 44. So 44 divided by 44 is 1. So actually for this problem, your molecular and your empirical formula are the same. In another experiment, liquid heptane, C7H16, is completely combusted to produce CO2 and H2O, as represented by the equation below. The heat of combustion for 1 mole of C7H16 is negative 4.85 times 10 to the third kilojoules. Using the information in the table below, calculate the value of the heat of formation of C7H16. Okay? Well, if you look at the overall reaction, I am given the heat of formation of water, that's one of my products. I'm given the heat of formation of CO2. The heat of formation of oxygen is 0, and it's asking me to solve for the heat of formation of C7H16. Well, I know that my overall heat of my reaction is negative 4.85 times 10 to the third. So I can just plug this in, taking products minus reactants. Okay. I have negative 4,850 is my total heat. That equals one of my products, which is carbon dioxide, so 7 times the heat of formation of carbon dioxide plus 8 times the heat of formation of water minus the heat of formation of C7H16 minus, because remember the minus distributes, well that's just 0 anyways. Okay, so when you actually solve and calculate this, you get negative 191 kilojoules or negative 191 kilojoules per mole. So you get 1 point for using the correct coefficients, right? So the 7, the 8, the 11, though you don't need to show the 11 because it's actually 0. And then 1 point for the correct substitution into, so I'm a little bit confused about that point. I'm assuming it's just one point for the correct heat of formation of your liquid heptane. In D, it says a 0.0108 mole sample of heptane is combusted in a bomb calorimeter. So I had talked about in class how we always just use specific heat and not just your heat capacity. Well, I lied. This is an old problem, but nonetheless we can do it just using units. So don't freak out, you're okay. It says calculate the amount of heat released to the calorimeter. Okay. Well, if you look at the problem before, we were told that negative 4,850 kilojoules are released per mole of C7H16. Well, if it's 0.0108 moles, all you have to do is multiply them in order to determine how much heat 0.0108 moles of your heptane would release, since it's not actually 1 mole. So the answer you get is 52.4 kilojoules of heat's released, or you could say negative 52.4 kilojoules of heat. Okay? Either way you want to put it. The released implies that it's going to be negative. So you got 1 point for your correct heat released. In II, it says given that the total heat capacity of the calorimeter is 9.273, calculate the temperature change of the calorimeter. So I've got, if I just look at units, I've got kilojoules per degree Celsius, right? Degree Celsius is on the bottom, and then I just calculated my heat, the 52.4. Okay, so all you really need to do, since I'm just trying to solve for delta C, or not delta C, trying to solve for your change in temperature or degree Celsius units, all you need to do is take the 52.4 and divide it by your heat capacity. Or, I mean, it's the same step, but the reasoning behind it, not looking at units, but looking at the equation, your heat capacity formula is Q equals C delta T instead of Q equals MC delta T like it is for your specific heat. So the one thing we're ignoring here is mass. But otherwise, the entire thing, the rest of it's the same. So the answer you should get is 5.65 degrees Celsius. Okay? Keep in mind, if you got D wrong, then your work for II should be based off the value that you got in DI. Okay? So you got 1 point for that.